So magnetic effects of electric current. So I'm pretty much sure that each and everyone knows what is a magnet, correct? So obviously it's something which will attract the iron pieces. So that we already know, correct? But the chapter name, magnetic effects of electric current. So I'll be teaching you how the magnet, correct, and electric current are related to each other. Okay. So there is something called electrostatistics in physics. Okay. With that, we'll have a small interlinkage in the class 10 thing. Very small portion. So we all know what is the use of electromagnets, right? Right from the electric generator to electric motors, we'll be using what? Magnetic devices, correct? But we don't know what is the relationship between the magnetic current or the magnetic behavior of those things. So that I'll be explaining in detail in this particular chapter. So first thing is, already we have studied the basics in our lower classes, correct? A compass needle get deflected when passing electric current through a metallic conductor. Compass needle, a compass is there, correct? A magnetic compass is there. So when I pass electric current, there will be small deflection on this particular needle. Okay, so it indicates what there is something, some relationship between magnet and current. That is our first thing. Properties of our magnet, we all know what. Every magnet has got two poles, north and south. We and also know like poles will, I think in 8th standard we have studied. Like poles repel each other. Unlike poles attract each other. Correct? So that's what same thing. And if I freely suspend a magnet, it will be in what? North-south pole. It will be in north-south pole respectively. That's it. If I freely suspend a magnet. Then characteristics of magnetic field lines. Okay. So field lines will arrive from what? North pole and end into south pole. So north and south. Here we can clearly see it is north and south, right? Because why? Because south and north are attracted to each other. Poles will, unlike poles will, like poles will repel, unlike poles will attract. That's the reason here. It's up to you on how to interchange the things. So this is pretty much basic topic, and we can't expect any questions from these things. But one thing we can express is field lines are in closed curve. We can see everything here in what? Closed pattern. I'll just draw this for you. A closed pattern. Down also I can join. Okay, it will be in a closed pattern. Fine. Let me just clear it. So direction of magnetic field lines inside a magnet is from what? South to north. South to north inside a magnet. So from south pole to north pole it will travel. Okay. And the strength of magnetic field is shown by degree of closeness of the field lines. Field lines is nothing but the dotted lines which is there here, no? Yeah. The dotted lines here. I think it has gone too much far. Yeah, this one. If there are more number of dotted lines in this, again I'll draw here. There are more number of dotted lines in this, the stronger the magnet. Or it is very, very close. The dotted lines are very, very close to each other. It will be more stronger. If the dotted lines are not, there is a gap. Just like this, there is a gap. Then what it is? Then it is not that stronger. So this is nothing but the magnetic fields of a bar magnet. It's in what shape? Closed curve. Correct? It's in closed curve. And then we got something called right hand thumb rule. Right hand thumb rule in the sense, let's imagine this pen as a wire. As a wire. Wire in the sense just like the laptop wire, or let's say the mobile phone charger wire, or whatever it is. It is a conductor, which means it's a conductor, meaning it can allow the current to pass through it. Correct? So what happens is that if I closely wrap this wire with my fingers, right? With my fingers. Can you see my thumb also here? Yeah, you can see my thumb also. I will. Yeah, now I think it's much more clear. Correct? So this wrapping, this is the wire, and this wrapping is nothing but the area of the magnetic field. So this is a current carrying wire. Just imagine this is a current carrying wire. And if I wrap it with my fingers, yes, this much area is a amount of magnetic field. And my thumb is there, right? It shows the direction of the current. My thumb shows the direction of the current. Okay. So this shows that in a conductor, what is there? Conductor in the sense anything which can pass current through it. There's a relationship between magnetic field and the current in a conductor. So these are just basic things. I told you again, we'll be learning all of these things in detail in the higher classes. One second, my screen is loading. I think you can see this. I think now it's okay. So that's what the same thing in right hand thumb rule. Imagine you're holding a current in the current carrying conductor in your right hand, such that thumb is pointing towards the direction of current. So my thumb is pointing towards the direction of the current. And the fingers wrapped around the conductor gives the direction of magnetic field. So this much area, my fingers are wrapping around, it gives the area of what? Magnetic field. Okay, and the magnetic field can be represented by concentric circles. I told you it's a closed curve. And one important thing, the more the current, more the magnetic field. So the current flow is higher, the magnetic field is also stronger. Then I told you this is, imagine this as my wire, the pen as the wire, correct? So if I'm passing a current through this wire, correct? This is a conductor, right? And this is a very small conductor. After 10 kilometer, can I experience the magnetic field? After 10 kilometer, can I experience this magnetic field? No. But if it is just 1 centimeter, can I experience the magnetic field? Yes. So magnetic field is inversely proportional to distance from the conductor. That's it. So the closer the magnetic field, the distance, we will experience what? There's a current, we'll experience more magnetic field. If the distance is very far, then we won't experience the magnetic field. And coming to this diagram, have you seen some coils actually? Coils, wire which is wounded. Suppose if this is a wire and we're winding one more wire, it becomes a coil, right? If there are more number of coils in a conductor, then there will be more magnetic field. If there are more number of turns, then the magnetic field will be more. That's all. So understand it in a very simple thing. And now what the example I told is this solenoid. So solenoid is nothing but in a straight wire, correct? I am winding the coil. So it will come in the shape of what? Cylinder. It will be the shape of a cylinder. So in a straight wire, I'm just winding out the coil, circular. So it will come in the shape of a cylinder. So this is called my solenoid. Okay. Direction of magnetic field. Inside and outside the solenoid. This they can ask as a question. Outside the solenoid, the direction of the magnetic field is from what? North to south. And inside it is from south to north. And what is the use of the solenoid? So solenoid is nothing but what? A wire in which I am wounding some coils in the shape of a cylinder. It can attract the iron piece, a soft iron. It can attract. An electromagnet. Electromagnet is nothing but it's a temporary magnet which I can easily remove the magnetic property. Okay, it's a temporary magnet so that it can easily be demagnetized. And some properties they are given. Polarity, that is south and north pole can be reversed, and it's generally a kind of a strong magnet. Permanent magnet. So electromagnet is a temporary magnet. Permanent magnet, I cannot demagnetize easily, and it has got more strength compared to that of a temporary magnet or electromagnet. And south pole and north pole are fixed. I cannot reverse it. Okay, and generally it's a weak magnet. Let me see this is an experiment. Yeah. Fleming's left-hand rule. So for this experiment, we have to know three fingers. Correct? One is my thumb, my forefinger, and my middle finger. So my thumb represents direction of motion of the current. My forefinger represents direction of field, and the middle finger represents direction of electric current. So what is it? If my forefinger, the L shape is there now here, the L shape. So my forefinger represents direction of magnetic field. Middle finger, my middle finger represents the direction of current. Yes. Then my thumb will move to the point of motion of that particular object. The motion of the current is there, right? Yeah, the object. How the object is moving. And please note that which is perpendicular. My magnetic field and current is always what? Perpendicular direction of force of the object. Okay. So magnetic field is there. Then my forefinger is what? Current. My forefinger is magnetic field. My middle finger is what? Current. Then the object will move towards what? The motion of the force of that particular. So just to tell you in this, we can clearly see here only one thing. My forefinger represents the direction of magnetic field. Correct? My middle finger represents the direction of motion of the current. Suppose if any object is there, yes, if the object is moving, it moves in the direction of what? Force created by magnetic field and the current. The thumb shows the direction of motion of that object, particular object. And where do we apply this? MRI scanning, magnetic resonance imaging. That is MRI scanning, we'll use it. And galvanometer. So we all know that ammeter is a device used to measure the current, right? Voltmeter is a device which is used to measure the voltage. So galvanometer is similar device which is used to measure the presence of current. An electric motor. So there is something called motor and generator. Generator gives us what? Generator will give us electrical energy. Correct? Generator will give us electrical energy. So conversion of mechanical to electrical is called generator. Motor. For switching on the motor, what we have to put? We have to put on switch, right? Electric energy to mechanical energy is motor. So just like that, you remember it. The motor and generator. And in a motor, there is something called commutator. How to remember this? Commuting. Commuting means what? Transportation. Correct? So commutator helps in the transportation of current throughout a circuit. That's all. Okay. Next one is armature. This also we know. Armor. So in the war field and all, we'll go, not we, in the olden days. Correct? They'll wear armor and go, right? Yes. So the body of that particular motor is protected. The coils, the slip rings, the screws, everything. Everything in that is clubbed together, right? It's clubbed together in the armature. So I think now you got the idea. So with that basic point of view, we have to read this. Use of motor, we know where it is used. Correct? So that is something. Electromagnetic induction, it's a separate topic, so which I will be sharing it to you later. Fleming's right hand rule. Just like we had left hand rule, we have got a right hand rule. In right hand rule, it shows that same thing, but in left hand rule, forefinger was what? What is the forefinger? Same thing only here. Fleming's left hand rule and right hand rule is almost the same. Correct? Right hand rule, what is it stating here? The magnetic field, the forefinger is what? The magnetic field, and the middle finger is the current in the induced inductor, and thumb shows the movement of conductor. Thumb shows the movement of conductor. A brief explanation I'll give you about electromagnetic induction. Okay, a brief explanation. If I place a conductor in a changing magnetic field, a magnetic field is there. You can see the magnetic field here, right? If a conductor is placed in the changing magnetic field, a small current is induced in it. Induced in the sense that particular conductor will experience a vibration. If we get an electric shock, suddenly we will tend to vibrate, right? That shock will be there, no? That's why it's called electric shock. Similarly, if a conductor is placed in a magnetic field, it will experience a current induced in it. It will experience a shock. That is called electromagnetic induction. So this thing in detail, I'll be sharing it to you later. Because I told you this is a very basic chapter, but the importance is huge. So this is explained by means of what? Fleming's right hand rule. Forefinger, magnetic field. Middle finger, direction of current. My thumb shows the movement of the conductor. Yeah, once it experiences a shock, the conductor will experience a movement or a jerk. That's it. Generator, I told you. When do you use generator? To get electric current. So here, conversion of mechanical to electric energy is called electric generator. And then there are two types of current. alternating current and direct current. In India, we use AC current. I'm sure that everyone in most home, there is something called inverter, correct? Whenever the power is not there, inverter will become automatically on, which means what? Inverter stores DC current and gives out AC. Inverter converts DC direct current to AC current. We cannot store alternating currents are variable current. It will vary. It will vary. Direct current means if I'm getting only 5 ampere, I'll get only 5 ampere. Alternating current, I'll get 2 ampere, 1 ampere, 5 ampere, 6 ampere. We can't say anything. We all experience low voltage some point in our life. Correct, in homes, low voltage and high voltage. That is because in India it is alternating current. But if you go abroad, let's take the US or into the other countries, we might have DC current here, underground cables. Here we got all the poles and everything, right? Again, I told you this is a very detailed thing. This is again a separate chapter in your class 12th. So I told you disadvantage AC cannot be stored. Direct current. I told you in inverter we use what? Direct current. DC to AC. Direct current to AC. The conversion of DC to AC is what? Inverter. That is not there in the syllabus, but just I told you. Our battery, storage cells, all of mobile battery, the remote battery, everything is direct current. Domestic electric circuits. So this is very important. Again, there are three types of wire. Live wire, which means current will pass through it. That is with red insulation. Neutral wire, that is negative. That is with black insulation cover. Earth wire. Earth means green. So these are the three kinds of wires used in our home. And the potential difference is 220 volt. That's the thing. Short circuit. Okay, short circuit when it happens is when this red wire, that is my live wire, comes in contact with neutral wire. Correct? Yes. So the resistance of circuit will become low. So which will result in overloading. That's why we get the burning and everything. If it is overloaded, then it will burn off. Overloading in the sense, suppose let's imagine a student can only listen for about 15-20 minutes. But if the lecture goes for 5 to 6 hours, what will happen? There is a capacity for a student to learn, correct, or to sit in the class. If it exceeds that particular limit, it's called overloading basically. So just like that, a current has a certain limit. Okay, only this much current that particular uh, device or that particular system can hold. If it exceeds that capacity, the student in the class won't react. But here, in what will happen in real life scenario, the current is not like student, right? So it will blast. That's all. That's called overloading. So cause of overloading is mainly, again, if you had inverter in the home, you will come to know that if I use a fridge, not a fridge, let us take a mixie or any other or electric kettle, then the beep sound of inverter will be more because it causes overloading. Okay, and safety device for this is what? Fuse. A fuse separates. Whenever there is a fuse, it will cut off the main current. So electric fuse, earth wire. Earth wire is nothing but if you do earthing in our home, the maximum voltage, it doesn't allow for the short circuit. It allows the maximum. It allows for what? The maximum voltage to be passed to the earth directly so that it will save the burning because earth acts as a large capacitor which can hold maximum voltage. Then there is something called MCB, miniature circuit breaker, which is nothing but the bigger form of electric fuse, MCBs. So that's a chapter, guys. So thank you then. Thank you to everyone.